Good morning, good afternoon, and good evening, everyone. Thank you all for joining us today. My name is Irina, and it's my pleasure to welcome every one of you. We are fully committed to being a strategic partner of tinyML and supporting tinyML community. And today I'm thrilled to be organizing organize another tinyML meetup here in France. Allow me to introduce my colleague, Francesco Paci, who brings a wealth of experience in working on low power applications. And Francesco will be joining me and moderating today's talk. To make this event even more special, we have a fantastic guest with us, and Francesco will introduce him in a while. Before we dive into the discussion, I want to express our appreciation to our sponsors, because their support has made this event possible, and it's vital for the advancement of tinyML. So let me just go through my usual slides. All the sponsors, I would like to thank them all: AIZip, Analog Devices, Arduino, ARM, Compass Marketing, Edge Impulse, Greenwaves Technologies, Groovity Incorporated, IBM, Imagilab, Inatura, Microsoft, Nota AI, NXP, OctoML, Wixo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Syntian, TDK, and others. Let me mention platforms of tinyML community. Of course, it's the LinkedIn page where you can find the very live discussions of all the members, and meetup.com, where you can see all the future and upcoming events and can sign up for our future talks. Don't forget to check a YouTube channel. By the way, the recording of this webinar will be published as well on this channel. So it's tons of useful information and beautiful presentations. You can find them all there. I would like to mention a physical event that's going to take place in Amsterdam this year in June. You can find more information on tinyML website.
Yeah, thanks, Irina. And so today we welcome Jens Wilhelmsson, which received his master's degrees on complex adaptive systems from Chalmers University of Technology. He joined IVL in 2019, and which is the Swedish Environmental Research Institute. And there he is an expert of data analysis and algorithms development, also for a flavor of machine learning. And he looks after the introduction of new technologies in projects that benefit the environment. So we leave now the stage to Jens, that will present one of his recent projects called Turbinator. So thanks, Jens, to be here.
Thank you very much for the introduction and the kind words. And thank you for inviting me, both to the tinyML community and to Greenwaves, of course. My name is Jens, as already mentioned, and I'm here to talk about the Turbinator. And it's I will get to everything, what Turbidity is and so on. And I looked at some other tinyML talks on YouTube, and I think that this will be not fully as advanced technologically as the previous ones have been. Very impressive stuff. I think it will be quite easy to follow. I hope so at least. All right. This is the topics I intend to mention. First, some quick words about me and environmental research institute that I work for, and Turbidity, which is maybe not so something that's familiar to everyone. Existing turbidity sensors, and some short history, and of course how the sensor works, and also some maybe discussion topics, some challenges, limitations, and so on. So first off, I work for a company in Sweden called IVL, the Swedish Environmental Research Institute. It's a non-profit research institute, independent, as you can see there. We do all kinds of research within everything from water quality, air quality, mobility, etc. It's a growing field, unfortunately, maybe, but it is. We do the ambition is to have 50% applied research and 50% consulting, and in which I do mostly applied research. And speaking about me, I think Francesco already mentioned this stuff, that I like AI. I like to apply AI to fields where they can make a huge difference quite easily. Where I work, I have a lot of great colleagues who are experts in different fields. So I get introduced to a lot of topics such as marine stuff, or I work with oysters and fish, algae, and so on. And applying AI in those kinds of fields makes a huge difference. The competition is a lot stronger working in self-driving cars than working with oysters and AI. And it makes a huge difference. Just a tiny bit of AI. No pun intended. All right, we're moving on. Enough about me. I'm going to start to mention something about the turbidity. And also, if you have questions, like we already mentioned, you can write them immediately in the Q&A, and we can take them right away if I notice them, or if Francesco tells me that there's a question.
Yeah.
All right, so turbidity is a measure of water quality, or a rough measure of water quality. It's a measure of suspended solids, but not as it's not very specific. It can be any kind of sediment that causes a high turbidity. And by high turbidity, I mean, as you can see in this, do you see my pointer, by the way?
Yes.
Yeah. As you see to the left here is huge turbidity, which means that the water is barely transparent. And lower turbidity means clean water. And what is this good for? It's good for, it's a rough measurement I already mentioned, which can be used within drinking water facilities or environmental monitoring or wastewater treatment, or you name it. It's very convenient. Right now, or it's often measured with these kinds of sensors. It looks like a tube. This is one from Campbell Scientific, and it works like this. That you have a photosensor and a LED, so it shines light and it measures how much light is reflected back. Quite easy. So the measure of turbidity is a measure of how much light is reflected back, and the more particles in the surface in the liquid, the more light will be reflected back. So it's quite simple. A bit more about current measurement techniques. This is a turbidity sensor that's been placed in. It looks like a lake or a sea or something, and it grew a beard, as it says here, also in the citation. This is a typical problem with measuring turbidity, because often you want to measure in places that does not have completely clean water, and over time this causes the sensors to be victims of fouling like this, and it doesn't take very long time before you maybe can't trust the measurements anymore. So you have to maintain the equipment a lot, and they're also quite expensive. I think one of these sensors in the last slide, Campbell Scientific, is about, I'm not completely sure about how the Swedish krona stands to the US dollar, but maybe between $5,000 and $10,000. So it's quite expensive. And the Turbinator, which I'm gonna get to now, is a lot cheaper. So the Turbinator, I have a timeline here that I'm gonna go through a bit because it could be interesting. It's the history of the Turbinator. It started out with my colleague Fredrik here. He got an idea when he were allegedly, while he was doing the dishes, he figured that, and he had a laser pointer available. So he took the laser pointer and shined it through the muddy dishwater. And he thought that I can tell that the different, how the light is diffracted in the, or spread out in the dishwater. It's a clear indication of how clear, of how muddy it is. And if I can see it, I guess that a camera and an AI should be able to see it as well. So he came up with the idea, and then we moved on. And first step was to verify that this works in a lab. So here you can see a laser beam traversing through the surface. And then we figured where to put it. And we had worked a bit with the stormwater systems before, and we know something about them at least. And it turned out that this is a very convenient position to put a sensor with the kind of advantages that the Turbinator has. We started building some prototypes based on off-the-shelf hardware. This is me and a colleague of mine putting one in a couple of years ago. Not so tiny ML, it's very heavy. And I will get back to this, but we started collecting training data also. On top of this, like a cable that's connecting to an expensive Temple Scientific turbidity sensor inside the stormwater well here now. It was very hard based on the disadvantages that I already mentioned to collect training data. So instead, we wanted to we started collecting data from a constructed facility in which we could control everything and maintain everything. So we built this in Stockholm. And then later, we got in contact with Greenwaves, which gave us contacts to another company called eWare, which helped us design and build new prototypes because we couldn't build them in the basement here anymore. We got to some neural networks. We managed to verify that it works. Very good. And then we're getting closer to the present. We got to learn about quantization from Greenwave. And we also got some prototypes delivered and also patent approved. And here I put the patent from America. They're very good at creating these kinds of documents. They look very fancy. And then quite recently, we deployed a couple of prototype sensors in Gothenburg. So that's the full story. And now I think everyone is curious to know how it works. And it works as follows. We put one of the turbidity sensors like this in a stormwater well. And of course, this is supposed to be the stormwater well, and here's the water surface. We have a camera here. We have a laser here. And when taking a measurement, we turn on the laser, we take a photo, and we turn off the laser. Photo looks something like this. Here is where the laser hits the surface. It's coming from the left here. And quite easy, by some simple trigonometry, we can find that the water level is going to be here. And then we take the information of the laser, we crop it, and we send it to our neural network, which gives us a turbidity 10, perhaps. And here's just a quick slide of, I mentioned that we position and find the laser dot. This is actually also one of the challenges right now, because we have a full-size image of the camera. It looks like this. And then we know that the laser dot is always going to appear within, it's going to traverse in this direction. So we can immediately crop like this right away. But it's only this very small part of the image that's input to the neural network. Of course, how big it is depends on how far from the surface it is. But there are some technical challenges here. Finding the laser dot, of course, just finding the brightest point in the picture is what we're doing right now. It's very easy and simple and so on. So but it has some disadvantages. So I just wrote down some bullet points here. And if you have any clever ideas how to do this and not keeping the image in the memory and so on, you can contact me after and I will gladly listen. All right. I mentioned something about the distance to the surface also. It complicates things because two images of the same turbidity but taken from different distances are going to look different. And this is going to be the case in our sensor, because obviously the distance is going to vary, and we're going to put the turbidity sensor in different wells that is different depths. So we need to collect data because if we're going to train a neural network to recognize what turbidity is what, we're going to need to collect data not only of all possible turbidities, but also of all possible distances. So we have 2 dimensions in our data collection. And I mentioned previously that it's quite hard collecting training data for this type of thing in real stormwater well, because we can't control the turbidity. We're going to get a super biased training material. So instead, we built our own stormwater well in Stockholm. It looks like this. It has sewer water coming in here, controlled by a pump, which we can program to whatever we want. And we have clean water here, and we mix it, so we get a homogeneous liquid, quite disgusting homogeneous liquid. And then here we have our turbidity sensor, the expensive one that we have to maintain a lot. Up here, we built a motor-driven winch. So instead of making the surface vary, we design it so that turbidity sensor can move up and down. And by doing this and varying both the distance to the surface by the motor here and the pump here, we can gather a lot of data. So here is a GIF I made, and this is the development. I call it the data coverage matrix. I'm not sure if that's the real term, but since we want to train a neural network to know the turbidity, we're gonna have to see how does the turbidity look at all different turbidities and all different distances, and we need to keep track of that. We don't have any gaps in our data. So this is so in this image, each number is a number of images for that particular combination of turbidity and distance to the surface. So we wanted to get as many images as possible, but also a good coverage of both turbidity and distance. So this, I think, is a couple of weeks data collection last summer. But we also get a lot of junk. There's always going to be situations where we find the wrong laser dot in image. There could be some reflections. It's currently only working when it's completely dark. So there could be a lamp on, whatever. No water. It's a number of reasons could be causes for us getting a bad image. So we solve it by training a separate neural network that we train to identify if image is good or bad, simply. Is this similar to the good training data, or is it not? And we're going to classification of that. I'm going to get back to that. Now for the neural networks, a bit more interesting now maybe. So I already said that we have the turbidity depending on both the image and distance to the surface. And we also need to be able to tell if the incoming image is worthy creating a turbidity prediction. And I maybe should mention why we need to know this, because since we put our sensor in stormwater wells and process everything on the sensor in the well, we send the result, we send the number and the turbidity back to ourselves through our receiving platform. And because we can't send images, it takes way too much energy to send images. So that's about the tinyML edge neural network stuff. So this is our requirements. By this, we figured we're gonna make a multi-input model. We have both the image and distance to the surface as input, and we're gonna have two outputs as well, both the turbidity and the indication of image quality, which is simply good or bad. Because we also send the good or bad, so we know if we can trust turbidity prediction or not. We made it look like this. This is maybe some of you recognize this type of image from Netron. Very convenient to visualize the neural network. We have an input over here, that's the image. And another input here, that's the distance to the surface. We do some convolution here. This separate lane is for checking if the image is good or bad. We have a logistic output over here. And in this lane, we use the convolution and combine it with the input distance to the surface. And we have a image and distance regression head over here. Then we get turbidity here. So this is the neural network that we're gonna use, or we're using. And also, I should mention that, or maybe I already did that, for a long time, the whole thing was just based on my colleague Fredrik's hunch that it should work, but he was right. It does work, and which we of course suspected it. And this is a scatter plot of our validation data when we trained on a part of the data in the based from Stockholm, the well that we built, the lab facility. So here we had a predicted turbidity on the x-axis and the real turbidity on the y-axis. So we have a mean error of around 10–15%, and which is, I think, is very good. Maybe not in a lab, and we have lab samples and so on. They have a lot better accuracy, but keeping in mind that we're not touching the water and it can be placed outside and so on. We're pretty happy with it. And something that has been a bit surprising here, a little bit black boxy right now. We haven't investigated a lot, but I thought that the longer the distance to the surface are going to have worse accuracy. And we can't see that here, or at least I can't see that here. That would mean that the darker dots here would be further away from the dotted line in the middle. That would mean that our high distance to the surface images have worse accuracy, but I can't see that. That's quite surprising. All right, that was it about the network. I'm going to move to the tiny part. And as I mentioned, our main requirement here was that we have to be able to leave the sensor outside in a stormwater well for a very long time, as long as possible, years maybe. We can't have maintenance, we can't have battery charging, So because sometimes the stormwater wells are placed in the middle of a highway or something, and it's very expensive to, if it doesn't work, we can't just go and pick it up. So this requirement, of course, gives that the neural network has to be able to run on the sensor and consume very little power or energy. Here's where Greenwave comes in. Very happy about that. Without Greenwave, it wouldn't have been remotely possible. I tried building everything on a Raspberry Pi in the beginning. It works, but it drains the battery. So big difference using the GAP8 from Greenwave, which is a ultra low power AI processor. And I'm not going to talk too much about it because I know Francesco is listening here and he knows 1,000 times more than me about this. So also jump in, Francesco, if I'm saying something stupid.
No, it's perfect.
Yes. Here is by the way, the GAP8. And I think it's I'm not really sure how big it is, but I think it's a couple of millimeters. Or at least the GAP9 is a couple of millimeters.
Yeah, that's a bit bigger. Yeah.
Yeah. All right. So here's the GAP flow. This is Greenwave, taken from Greenwave's website, and we started out having TensorFlow models, and then we converted them to TensorFlow Lite models, which is the starting point of the GAP flow, which is the tool chain of how to make our neural networks run on the GAP8 processor. It contains NN tool. Here we did model optimization, specifying the inputs and so on, and quantization, which I will mention a little bit more, and it creates something called autotiler models, which is another block here. From autotiler, we get C code, which can be used to create the flash files that we put on the GAP. So it runs. And if you have any questions about this specific slide, you can ask Francesco. So I'm gonna mention a little bit more about this topic. I think it's maybe a popular topic within tinyML, moving from floating point to integer precision. Since the GAP8 uses integer precision, we need to quantize everything because we're starting out with floats. I think that the new GAP9 works with floating point. Is that correct, Francesco?
Yeah, it also works with floating point. Yeah.
Yeah. Maybe it's still a good idea to use integers or in battery terms. I don't know. But anyway, we get some loss in accuracy because our model, you saw it, it's maybe not huge, but it still has a couple of 100,000 parameters. And we want to round everything in an efficient way, not to lose too much accuracy. It's not perfect right now. We have not, as I mentioned, or I say in the slide also, have not made a very big effort in minimizing the accuracy drop, but we do experience some. But also, all photos we take on each sensor are stored locally. We can't send it due to it costs way too much energy, and it's not even possible using our communication protocol. But everything is stored on the sensors. So every time we go and pick the sensor up, we can we can take the images from the sensors and we can post-process it on our servers and get better accuracy. And it's also good for our development as we get the images back. Here is just a plot of comparing the turbidity predicted using GAP on the sensor, and when we picked it up and brought it home and post-processed it, I should also mention here that it looks very good here. It gets a bit out of range here at high turbidities. But if someone was paying attention back at the GIF I showed for what data we collected, we didn't go over 80 turbidity. So that's the current limitation. So everything above this line is an extrapolation of the neural network, meaning that I wouldn't trust it. So here is probably our detection limit right now. All right, I touched a little bit upon the topic of sending data. We're using this module, a Quectel module called BG77, sending data over narrowband IoT, which is made for IoT stuff. And it uses we tried both using the LoRa on the long range IoT network, whatever it's called. LoRa uses local gateways, so we have to connect everything to all these gateways that has to stand everywhere. And I know that there's a lot of big companies that's creating LoRa networks, which is great. And they do have, LoRa do have longer reach, but narrowband has better penetration of structures, which is quite good for us since we put these heavy iron lids on top of our sensors. And from here, it can be quite hard to get signal out. So when for narrowband IoT, not only because of this, but also because it's very convenient because it uses the cellular network. So we only have to think about putting in SIM cards in the sensors or eSIM cards. So as long as we have that for the country we're in, it's going to be more plug and play. All right, yeah, as I mentioned, we have some connectivity problems due to these thick lids. I will mention a little bit about that in a second. Right now, actually. So now I told you everything that's good about the sensor. It's cheap, how it works, and why it's cheap is because it's everything inside is very cheap. It's a camera and a laser, and the GAP 8 is not expensive either, relatively cheap, and so it gets cheap. Also, it's not a submersible sensor. It can handle water, of course, and it can be covered in water, but it's not submersible as in the very expensive current turbidity sensor, which saves a lot of money in construction. But as I mentioned, still the reception can be quite bad in stormwater wells, and it's quite energy consuming to send data, and we have to choose wisely how often we send data. The environment in stormwater wells is harsh, and people pour things out there, or not so nice stuff either, and it could be rats and you name it. It's not so nice. We've had some problems with the classification. I wrote OK Nook here. That's the if we have a good or bad image, simply that part of the top part of the network where I showed the architecture. So you have to improve that, because there could be a lot of images that we can use, but still are not bad because we haven't seen really similar in our training data. So I will get back to that. Finding the laser dot is not as easy as I thought it would be, because we're so limited in what we can do. And of course, we can't send images. Our customers have asked for this, because we also have a flash, so we can light a flash and take what we call inspection photo. So, and that we also do. for each image that are classified as bad, we take a flash and a spectrum photo, which we can go back and look at, and we can see why is it bad, because that's information that our customers are interested in. But of course, when there's bad predictions, they would really want to get the image right away. But we can't send it, so we have to store it right now and show it later. And I mentioned data, training data. I think this is maybe a topic in all neural network things, that you always want more data. You want more data, you want better data, and we need more training data. We're going over 80 turbidity, for example, and covering larger distances to the surface. So more data, better data for both parts of the neural network. Some ideas for these different challenges. New antenna, maybe better. I don't know. We'll see. We've had some workshops about this, because it's not only our sensor that has problem communicating out from a stormwater well. Maybe we can have an external antenna that we can pull up and place closer to the lid or something. I think I asked right before this meeting, or a couple of hours ago, a partner of ours, but I have the perception that sending data are going to be the constraint in our how long the battery can last, because the GAP 8 and especially the GAP 9 doesn't take a lot of energy compared to sending, and it feels also like that part is getting better and better. The reduction from GAP 8 to GAP 9 was huge when I looked at the numbers in energy consumption, but the sending, there's a physical limitation in how little energy it can cost to send data. So we're always going to be limited to that, and so we have to think about that and choose how often we send data. But what we do right now is, of course, that we measure a lot more often than how we send. Maybe measure every 15 minutes, but only send all the data once per day. We can't do much about the environment in stormwater wells, but we can build the sensor so we can withstand the harsh environment. Here, more data, of course, always the solution. Easy, just throw more data at the neural network. Also, the current network has discrete output, or it doesn't, but we round it. Maybe we'll move to a bit more continuous indication of the quality. I don't know, maybe using some kind of autoencoder or something. We have some ideas, but since we're building everything and doing everything, we have to prioritize quite hard, and we're not very many people working. This has also been an interesting topic. Some of you may be sitting and thinking, why don't you just use another neural network with the localization so we can find the laser dot? It should be easy. And I agree, it should be easy. But then we have to input the whole image to a neural network. Right now, we are only inputting very small part of the image. And so I guess there's ways to work around this by maybe compressing the image or doing some clever stuff, but we have not figured it out yet. How to use neural network that can both find and predict the turbidity. Yeah, I mentioned that maybe we can add an expansion pack to the Turbinator, put it within a stormwater well, pull a cable up. Maybe not if it's in the middle of a highway, but if it's in a bit more convenient location, we can take a cable up, maybe have a solar cell or something, so which is also an antenna for us then. and we can start sending data or send images at last, because that will be popular for our customers. Also, this is an interesting topic, I think. As you saw, we had to build this huge construction thing and collect data and moving the sensor up and down. What about augmenting data? We can just generate this data. And we haven't tried it out yet. We've been discussing it a bit, and I think we can just create data, but it's quite hard to know if it's, how can we trust it? Because it comes with a, if we augment a picture of someone, we can quite easily say that, yeah, it's a person, it's a picture of a person, but we don't, no one knows how the turbidity of 150 turbidity looks, especially not if we haven't measured that high before. So I think maybe we will start augmenting data for interpolating. So if we know that what 70 and 80 look like, maybe we can augment the data for 75. But extrapolating, saying that this is an image of how it looks of 200 turbidity might not work, or we won't know. So we'll see. We'll try it out. That's that. I am almost reaching the end of my presentation here. I have some topics that I haven't mentioned that I'm going to leave. I haven't talked anything about what happens on the other end. I just say that we send data. So we're also going to have a receiving end. We have a data platform, which I took just a screenshot of a Grafana site here. Here we have some sensors, and we have a map where they are, and all the distance and everything. So this is a lot of work as well, huge work package. And also the topic of why are you doing this? And what can you achieve using 1,000 Turbinators? The ambition is for a city to be able to have maybe 10,000 sensors they can put everywhere in the future. And I should maybe not start talking about what we can do with all this data, but there are a lot of services we can build, like predictive maintenance and finding pollutants. The sky is the limit. But that's it for me. If you want to speak to me, you can always send me an email. And if you want to read more about the Turbinator, you can always go to Turbinator.se, which is our homepage. So yeah, if you have any ideas or development ideas or criticism, I'm open for that as well. So thank you.
Thank you. Thank you very much, Jens. So I have a few questions, and there are also a few questions from attendees. So the first one maybe is because I'm not an expert at all of all the well maintenance and for example how fast you need to react. So because you do these measures, but then is there a reaction that you should do afterward if something happens? Because it's also to understand why you have how often you measure. You mentioned at the end, but I mean, if measuring faster could be actually improve the system because you have to react. And I also maybe link this with a question that has been asked, which is it to be expected that the wastewater sample always has to be diluted before it goes inside your sensor? And it provides an example saying wastewater coming from a stormwater retention tank or directly from a wastewater treatment plant can be different.
I think there was a couple of questions there. So maybe the first one first. I think it was how fast you need to react. And it depends on what you use it for. It could be used for just say that you have a construction site in a nearby, which you have in all cities. You can keep track of if because often they use they dig and they pump up water, and they have maybe obligations to clean the water before they let it out in the stormwater system. And if you have if you're monitoring the stormwater system, you can make sure that they're following the regulations. And you can all and maybe there aren't, at least in Sweden, there's no strict regulations on smaller construction sites because it's so expensive to measure. So by putting a sensor like this, we can make it possible for the legislation to move further to put the bar higher for construction sites. So in that case, we don't really have to measure very quickly. If they're not letting something out that's really bad, then we have to catch it right away. But often it's often a matter of days, and even if someone pours something out in the stormwater system, we're not going to be able to stop it. Maybe we're going to be able to catch who did it by retracing where it comes from, but they're probably never going to be like a task force standing ready. But it's also, I should also mention that it is possible. We use on the MQTT stream, the communication with the sensor. We can make it send data and capture data more often remotely. So if we see that maybe a big storm is coming in and we want to have measurements more often or sending more often, where we can trigger that and we can tell sensors in a certain region or something to start measure right away. We need a lot of data right now. But of course, then we have to know that something is coming. I think there was another question about
So my understanding of this question is more related to the fact that you have to, because you said that you have to dilute the water before I mean when you collect the data, and so the way I understand the question is that after, so you cannot measure, you can measure up to a certain point of turbidity, not after that.
I think from this slide, I guess.
Yeah.
Here we dilute the sewer water with clean water. And of course, in this setup, in this image, we can't move higher in turbidity than the sewer water is, of course. But we're building a new testing facility right now, which we're going to be able to add turbidity by ourselves and close the loop. So then we're going to be able to go higher in turbidity. So, and this is of course only for collecting training data. And I think also there was a question about what about sewer water? Does different turbidity in different waters look different? Was that a question?
It was an example. It was not really clear, but maybe if you have, I mean, if you have a hint on.
And I can only say that we're investigating. It feels like there should be a difference because turbidity is such a rough measure, and if it's a white or black liquid, it should be different. I haven't noticed it yet, but it should. We'll see. We have a lot of tests to do.
Okay, then I mean, there's another question related to DNN architecture. I believe, I mean, the question is, what is the architecture that you use? I believe it's a kind of custom architecture, but maybe you explore with different architecture or you can at least mention where this design of the architecture came from.
It's a custom architecture. We started out with testing out a few like classic architectures, like mobile net and so on. Wanted it to be lightweight. It's very popular, but I thought it feels too big. It's too competent. You saw our images. It's red and black, or actually it's black and white in sensor. But MobileNet it's so good. We don't need it to be that good. So we designed our own network, and we just used a couple of convolution layers and did some testing. How many do we need? How do we lose accuracy? Yeah, it's not that complicated. And of course, I think I hope I don't get a question of the regression here. This is one of the hardest part, I think, in designing this network. How do we? And I Googled a lot of this, and I wish that ChatGPT existed when I were doing this, because I would have asked it a lot. And there's not many people doing like concatenating like numeric data and image data and creating some kind of image numeric regression combined. So I've been doing a lot of guessing here and trying to think logically. But so as you see, we're just doing some convolution here. Then we're doing just some dense layers, combining the input here with the output from the convolution. And this seems to work, but I assume that there are 1,000 better ways to do this. Yeah, hard to tell.
Okay, yeah, that's because also you have to weight differently the data. Yeah,
exactly. How to know, I don't know.
Okay, then I have another question related to the network itself, which is, have you used explainable AI to find out which part of the image is used by the neural network to estimate turbidity? Which is, I believe, also if you had a look at data inside layers and I mean, what happens where?
I have not actually. It's on my crazy long to do list. But it's and it would be very interesting. But there's been so many other things to do. So when we saw that it worked and we gave good predictions, we moved on to making it work on the GAP, and then we moved on. But it would be really fun to investigate to get like a heat map or something with the explainable AI and look at some intermediate.
Okay, thanks.
Great stuff.
Okay, thanks. I have time for the last question.
Yes, go ahead.
So there is a last question related on energy consumption. So maybe you roughly mentioned that. But if you can maybe detail, I don't know, with relation to a battery, how long will it last? What is the energy consumption of the model with relation to the communication, or if you have some more details on that.
Yeah, I wish I had. I asked someone about this 3 hours ago because and we didn't have time to actually measure how it compares. So I wanted to actually change my slide just before, because I always had a gut feeling that it is the sending of data that really drains the battery. But I don't have any numbers, so okay. I'm not sure.
Okay, and then there is a question related to NN conversion to GAP8, the last one.
Okay.
So how did you convert your TF Lite NN to be compatible with GAP8?
I used this toolchain here, the GAP flow. So started with NN2, which is at least for me, I think it was a command line tool, and then I just took the steps here on and on. And also I had a lot of help from Francesco and your colleague Marco helped me out with this.
Yeah, maybe what is interesting is if this model is compatible with other processor, or is it just specific for? There's another question. Yeah.
Oh, if it's specific for the GAP or for the, I don't know, actually.
But I believe that it's, a generic model that could be implemented on other.
Yeah.
On other. Yeah. Okay.
Yeah, I guess.
Okay, thank you. So I think we don't have any other question, and we are running out of time.
Thank you so much, Jens. Yeah. Let me take a lead on the screen. Today's discussion, let me highlight and one more time say a couple slides, say a couple words about the sponsors. Edge Impulse, Qualcomm AI Research, Syntian, Renesas, AI Trios, Analog Devices, Arduino Pro, ARM AI, Inatera, Microsoft, SenseML, ST, Synaptics, and Silver Strategic Partners, AIZip, Compass Marketing, Greenwaves Technologies, Groovity Incorporated, IBM, Imagimob, Nota AI, NXP, OctoML, Polyon Technology, Wixo, Schneider Electric, Silicon Labs, TDK. Thank you very much, everybody.